Okay, good evening, all of you. So, today we'll start. Am I
Very
audible?
good.
And page is visible. Both you can say.
Yes,
Hello.
ma'am.
Yes,
Yes, ma'am.
Okay, fine. So, coming to the unit 7, which is your flame photometry. Okay. Till now, we discussed UV visible spectrometry, then fluorescence, IR. Mostly these all are your molecular spectroscopy, okay? Where molecule is there, molecule excitation is happening. Then you are having the electronic energy level, then vibrational energy level, rotational energy level. You heard about all these things. But what is the specialty of today's class or hereafter? This is your flame photometry. We are going to start. Before that, you need to understand what is atomic spectroscopy. Because till now we are studying molecular spectroscopy. Molecular spectroscopy make it clear in your mind that you are having electronic energy level, then vibrational, then rotational. All are quantized, means they are having a particular energy level. Their level is having particular energy quantized. That is why when you are doing electronic transition, going for the electronic transition, you are seeing broad bands for UV visible or fluorescent spectroscopy. But here, for the atomic spectroscopy, the vibrational and rotational energy levels are not quantized. It is having a discrete energy level. So that is why these things will not come into picture. So mostly the atomic spectroscopy you will be getting in lines or sharp peaks you will be getting, not the broad ones. But sometimes due to that Doppler effect, you might have had Doppler broadening and other factors. Broadening to some extent also can happen. As I was telling you, always there is, if a specific rule is there, then deviation from that rule is also available. Okay, so let's see the introduction part. So in this course, you have so far learnt about your spectroscopic methods of analysis based on the molecular spectroscopies, what I was telling you. So in the present and next few units, why I am emphasizing this introduction part, because you need to understand this, because in subsequent classes, these two classes as well as next two classes, you will be reading completely on this atomic part only. If you understand from the beginning, then it will be very easy for you to the next consequent classes. And I think by this time, you know all spectroscopic methods are very different. All spectroscopic methods are unique because they are designed in such a way that you will be getting a good intensity peaks as well as your signal to noise ratio. Signal to noise ratio means, if a layman way, if you try to understand, then suppose you are using a Bluetooth. Nowadays you will be seeing noise free uh, noise cancellation parts are coming into picture. Why so? Because noise is less means clarity will be more. So that is why all spectroscopic tools, slowly also there is development to all spectroscopic tools. So now you can see in the present and next few minutes, you will be discussing about your spectroscopic methods based on the atomic spectroscopies. In atomic spectroscopy, the element present in a sample is converted into gaseous atoms. This point is important. In atomic spectroscopy, the element that you want to study, first it will be converted into gaseous atoms or elementary ions in a process called atomization. This step is very important. First, you need to do atomization. After that, which may be brought about by any of the available methods. For this atomization also, some methods are available. Subsequently, we'll understand that. So the absorption of radiation by the vaporized atoms in the ground state or emission or fluorescence emission of suitably excited state forms the basis of different type of atomic spectroscopies. So the main basis is okay, you are doing atomization, then you are just studying like the other molecular spectroscopy you studied. There is ground state, there is excited state, absorption process is there, emission process is there, fluorescence is there, everything is here also in atomic spectroscopy. If you have not understood the molecular spectroscopy, then it may be little difficult to understand atomic spectroscopy. But however, one more point I want to tell you, till now whomever have not understood the molecular spectroscopy, by understanding atomic spectroscopies also you can correlate the molecular spectroscopy. The only difference is here atomization process is happening, then subsequently what you are doing, subsequently you are exciting, you are getting emission, everything is happening. But here since your vibrational and rotational energy levels are not quantized, you are not going to see broad peaks like the way absorption emission you are seeing. Okay, so uh, this unit will concern about the flame photometry, which refer to measurement of the electromagnetic radiation in the UV visible range emitted by the vaporized atoms after they are electronically excited by the thermal energy of flame. This unit is flame photometry. Okay, flame photometry. So next will subsequently you will understand it in more and more clarity way. You know very well whenever we are discussing this spectroscopy part, slowly in the beginning if you are listening me carefully, then subsequently while coming to the instrumentation part you will be halfway you will be understanding everything. Okay, then after that application parts are there. So this is the basic protocol for all the spectroscopies. So it is this flame photometry is a simple and rapid and inexpensive method for routine analysis of alkali and alkaline earth metals. Okay, mostly this flame photometry technique we use for analysis of alkali and alkaline earth metals like sodium, potassium, lithium, calcium, barium in environment as well as clinical as well as biological samples, specifically in biological fluids and tissues. Just vaguely, if you want, I want to recall you that this flame photometry technique, you know just 10% about that before also. If you remember your practical classes, that the detection of sodium, potassium, then through using charcoal cavity, you are keeping that. Then you are utilizing that flame to see whether it is yellow color, whether it is some other color. Have not you studied that? So that is what is the basis of this flame photometry. But that is not enough part. There you were not using lens, now monochromator was there. Very precisely you were not studying that. So this is the thing I was telling. As a chemist, you would have performed this flame test in your laboratories during graduation time, during plus two time maybe, but during graduation time, you must have done this for the identification of some elements, especially your alkali and alkaline earth metals in their salts. You have already studied this. So you could have observed the beautiful colors imparted by the elements to the flame. The color is a consequence of emission of radiation by the gaseous atom. Okay, the color which you saw that time, it is due to the emission of radiation. But up to that time, you didn't know this. What is this emission process is? My teacher will tell you, just put the salt in charcoal cavity and do the flame test. Bas, you just blow the flame. Color is yellow, so it's sodium. Color is this, so this is that. But from where the color is coming? The color is a consequence of this emission of radiation of these gaseous atoms. Okay, so the emitted radiation can be analyzed in terms of the wavelength and the intensity and can be used for the identification and quantification of the element. Whatever this emitted radiation is coming out, it can be used. Its wavelength, its intensity can be used for the identification and quantification of the element. So this forms the basis of atomic emission or flame emission spectroscopy. So one of the types of this is atomic spectroscopy. So flame photometry is one of the type of your atomic spectroscopy. Okay. So from where the origin is, like I was telling you, like in case of molecular species, here also you are having ground state, you are having excited state, then you are having it is when it is coming to the lower energy level, there is emission also. Okay, and there is a spread of wavelength of the photon absorbed or emitted versus intensity, which is known as your spectrum, like the way we discussed during the molecular spectroscopy. Here also you are going to get everything as such, but the thing is, remember that since the energy levels are not quantized, you are not expecting broad peaks, rather you are expecting sharp lines or sharp peaks, and provided there is no Doppler effect, there is no other uh, pictures are coming into uh, discussion. So, okay, in molecular systems, see, in molecular systems, the rotational and vibrational motions are also quantized in molecular spectrum, a molecular system. Besides the electronic energy, electronic energies are quantized, means your each electronic label E0 or E1 or E2, or you say designate is at S0, S1, S2, they all have definite energy like NH nu, okay, NH nu, H nu, 2H nu, 3H nu, like that some it is having specific energy. But different type of, similarly, your rotational and vibrational motions are also quantized for molecular systems. Different type of electromagnetic radiation, that is microwave, IR, UV visible, are required to cause the transition amongst these levels. So various radiations required for the transition. On the other hand, in case of atomic systems, only electronic energies are quantized. The transitions being brought about by the UV visible radiation. Here, IR or microwave region radiation is not playing role because IR region radiation is falling on matter, then vibrational transition happen. Here, vibrational energy levels are not quantized. If microwave radiation falls on matter, then rotational energy level transitions happens. Here, rotational energy levels are not quantized. So here, only UV visible radiation can bring some changes to the atomic spectroscopy or flame photometry technique. Okay. So this is what is the thing. In atomic spectroscopy, the elements present in a sample are converted into gaseous atoms or elementary ions, which the process is known as atomization. And this process can be uh, attained by various ways, like by applying flame or electrothermal or furnace method, then inductively coupled argon plasma, direct current of argon plasma, electric arc. So depending on your suitability, depending on your lab facilities, as well as depending on the nature of the sample you want to study, you can do atomization by using flame or by using electric arc or using any plasma technique also. Okay, that you can do it. So these methods basically accomplish the atomization process in different temperature ranges. Once in the vapor phase, the atoms of the elements interact with the radiation and provide information about themselves. Okay, the interaction of radiation and the matter can manifest itself in terms of absorption, emission, and fluorescence emission. Accordingly, we have atomic absorption, emission, and fluorescence spectroscopy. What is I was telling you, like that in molecular spectroscopy. Here also we are having atomic absorption, atomic emission, or fluorescence spectroscopies. So these are the normal processes involved here. But in subsequent like units, completely there is description of AAS, AES, and AFS. These are all one unit for you in the next units. But here there is glimpse of idea about these techniques. So atomic absorption spectrometry, what is that? In this method, the atomic vapors containing free atoms of an element in the ground state are subjected to UV visible radiation source emitting a characteristic frequency of the element present in the atomic vapor. Okay, the radiation is absorbed and the intensity of the radiation is attenuated. The absorbed radiation causes excitation of the electrons from the ground state to excited state. There is absorption of certain radiation, then similar to your molecular part, molecular spectroscopy. Here also there is excitation from ground state to excited state. So the extent of absorption is a quantitative measure of the concentration of atomic vapors of the element in the ground state. We have already read the absorption spectroscopy or UV visible spectroscopy. And there also, the extent of absorption is directly proportional to the concentration of the species that we are going to study. Here also, similarly, same thing. Means it is directly proportional. The absorption is directly proportional to your concentration. So that is this concept only helps you for quantifying, for the quantitative analysis. Okay. So it is an electronic excitation and the energy transition lies in the UV visible region of the electromagnetic spectrum. This is atomic absorption spectrometry. This is the basic principle of that. So what is this AES, atomic emission spectrometry? So in this method, a sample is normally excited by the thermal energy of the flame or argon plasma, or you can say electric discharge. First, what is happening? There is normally it is getting excited by thermal energy of flame or argon plasma, like that. The atoms in the sample, then what happened? Absorb thermal energy, then causing excitation of the outer orbital electrons. As the excited state is short lived, the excited atoms return back to the ground state after a very short lifetime. That is typically about 10 power minus 6 to minus 9 seconds. So this is accompanied by the emission of electromagnetic radiation, normally in the form of UV visible, uh, form of light in the UV visible region. That is why you are seeing the visible lights coming out of it. So the wavelength of the emitted radiation and its intensity provide quantitative as well as qualitative information about the analyte. So here you need to understand this AES and AFS, that is atomic fluorescence spectrometry. Okay, this one first we'll finish it. The atomic emission spectroscopy employing flame as a means of excitation is called flame photometry. Okay, the atomic emission spectroscopy employing flame means of excitation is called flame photometry. So it is used for routine determination of metals, mainly alkali and alkaline earth metals. This AFS, the gaseous atoms are excited to higher energy level by absorption of the electromagnetic radiation. Okay, absorption of the electromagnetic radiation and the fluorescence emission from these excited atoms is measured, like the way we saw fluorescence in molecular spectroscopy. So the main advantage of fluorescence detection compared to absorption measurement is greater sensitivity. That is what I was telling you in the last class. As compared to absorption, your fluorescence is very, very sensitive because this fluorescence signal has a very low background radiation. Background radiation means you can say background noise. In terms of your radiation, you are calling it as low background radiation. Okay, so this is the diagram which is showing you that there is transition, this one in the atomic absorption, there is excitation from ground state to excited state, that is absorption. Emission is the middle one, there is, that is de-excitation, and it is emitting certain photon. But see, what is here the concept is fluorescence is also a part of emission process. Okay, fluorescence is also a part of emission process, but emission, when it is some photon emission is happening, it can happen to any state, normal emission. But in the last class, if you remember, my point that fluorescence always happens from the lower excited electronic state to the lower ground state. That is what is the real resonance fluorescence. Sometimes there is deviation. Sometimes there is deviation also where your non-resonance fluorescence happen. It instead of ground state, it goes to the other energized state. But however, it again comes back to this ground state through your non-radiative relaxation process. That is possible. Okay. So, as we have a number of methods of atomization, means electric arc you can use flame photometry. So, three different type of ways, that is absorption, emission, and fluorescence emission of measuring the radiation and a light interaction. So, there are a number of different type of atomic absorption spectroscopic method, atomic spectroscopic methods. Okay. So, subsequently, we'll be seeing one by one. So, what is the characteristic of this atomic spectrum? Slowly, whatever doubt is coming in your mind, slowly in subsequent pages, you will be more and more clear about that. You will find all the answers involved here itself. Your documentation, your this spectroscopic method material is given in such a way that if you read it carefully, see, And everything by line it has been described. So this is the characteristic of atomic spectrum. So in block 1 and block 2 on molecular spectroscopic method, that the molecular spectra are generally broad in nature. That is what I was telling you just 5 minutes back. So these consist of a number of closely spaced lines constituting what is called a broad spectrum. Number of lines were there due to your vibrational transition as well as rotational transitions, and it was giving rise to broad spectrum. The broad nature of the spectrum is due to a number of factors like the quantization of rotational and vibrational motions of the molecule along with the quantization of electronic energy levels. In addition, the width of the spectrum is also dependent on the sum of the instrumental parameters also. But mostly, since the rotational and vibrational energy levels are quantized, that is why you get a broad spectrum. In contrast to this above means molecular spectroscopy, the atomic spectra consist of a number of very sharp lines. It consists of sharp lines. Okay, the characteristic of the atomic species is this thing. We get a sharp line in the spectroscopy. It implies that these give rise to line spectra. The atomic spectra are generally much sharper because in atomic systems, the rotational and vibrational motions are not quantized, and the transitions are observed among the electronic levels only, electronic energy levels of the observing species. So this is a characteristic atomic spectrum. Generally, these are sharp peaks type, observance and wavelength. You are getting the sharp peaks here. This is the atomic absorption spectroscopy or spectrum. So similar to your molecular spectrum, you are getting a signal. That signal is having your position, certain intensity is there, certain width is there. So what you are doing? Last classes we had discussed that the band is having a certain position or width or intensity. Depending on that, we use it for the application oriented work like quantitative analysis or qualitative analysis. You do by seeing whether the position is shifting or not, whether the intensity is changing or not. I was telling you in the previous class that when you are using solvents, if you are increasing the polarity, then emission maximum is changing towards the right of the wavelength, means longer wavelength. So in that way, you can predict what is happening to the system. So similar to molecular spectrum, the signals in the atomic spectrum are also characterized in terms of three parameters. Okay, one is position, intensity, and spectral width. Position of the spectrum means if you are seeing a spectrum, it is having certain wavelength. It will you are seeing in a certain wavelength region. At the same time, you can say this peak maximum, whatever peak maximum you are seeing here, that is lambda max. I was telling you in the fluorescence class, that is your lambda max. So like in molecular spectra, here also the position of the spectral signals is determined by difference in the energies of the different energy levels. Here also you are having delta E is equal to your h nu, that is hc by lambda. So lambda is having your certain value to it. Okay. So this wavelength of radiation is characteristic of the atoms. of the particular element from which it is getting emitted. So wavelength tells you more about the position of the peak, position of the spectral peak. Okay, so these are the characteristics of signals we are talking about. So position of the signal you can predict from the lambda or lambda max, you can say. Then another characteristic of the signal is your intensity of the signal. So the intensity of signal depend on the population. We discussed about the Boltzmann distribution, if you remember. So population is more, concentration is more, means intensity will be more. But in concentration, if you are increasing so much, then also problem is there. Self-absorption problem, quenching problem. Yesterday we discussed everything about that. So the intensity of a signal depend on the population of the energy level from which the transition is originating, and the probability of such transition is increasing. Okay. The probability of transition will increase if your population in the ground state is more, and which is leading to or originating your transition to happen. So it is given by the Boltzmann distribution equation, where your n star and n zero are the number of atoms in the excited state and ground state. If ground state this thing is more, then you will be getting more good signal. Okay, so that is what is defining the intensity of the signal. So based on this Boltzmann distribution, there is one numerical. Numericals you must practice at home. It is given here. Then, as we are discussing, intensity and concentration both are proportional to each other. If concentration is more, then your intensity of emitted radiation is more. Then, spectral line width. This is another spectral characteristic of the signal. What it is? This is what this full width half maximum. So the lines are generally symmetric around the lambda max. Okay, the wavelength at which the intensity of emitted radiation is maximum. I was telling you, at lambda max, the you get more intensity of the spectral of the spectrum. So the observance is also the maximum at the same wavelength. So the line width is defined as the width of signal measured at one half of the height of the maximum signal. So this is what this I am not able to select this figure, but if you can see the middle dotted line is showing you the lambda max region, that's the maximum intensity region. And if you take a half of that part, then at the half of that signal, okay, height of that, you are going to get full width half maximum, which is saying you the spectral line width of a particular spectrum. So basically, you don't get this much broad band in absorption spectrometry. Okay, you get mostly narrow parts. But as I was telling you, sometimes there is collisional broadening, sometimes there is Doppler broadening, and due to uncertainty broadening, also you can get a little uh, broadband, but not the way you are going to get for the molecular spectroscopy. Okay. So, what is this principle of this flame photometry? So always you must remember the principle of all the spectroscopic method. You may get questions on that. What is the basic principle of fire spectroscopy? What is the basic principle of UV visible or fluorescent spectroscopy? I had gone through all the materials, whatever questions are there as SAQ, okay, all the answers were just near the before discussion itself. Before that, all the answers are already written over there during the discussion parts. So you go through the materials carefully before your exams. So the principle of flame photometry is the flame photometry is a method used for the determination of elements which can be easily excited. For example, alkali and alkaline earth metals. This method is based upon the measurement of intensity of radiation emitted in the visible region when a metal atom is introduced into the flame. When the metal atom is introduced into the flame, then atomization is happening, then it is going to the excited state, then coming back by emitting certain radiation, then you are monitoring that. So the wavelength of the radiation or the color emitted tells us what the element is, and the intensity of the radiation tells us how much element is present. So from the radiation you can predict what is that element is, and from the intensity you can predict how much amount of element is present. Means quantitative analysis. So basically what is happening, one nebulizer will be there, okay, where your mixing of the uh, what mixing of the substance which you want to study is happening. So these are the processes occur in the flame photometry or flame part, that is your teacher dissolution. The sample, whatever you are taking, we saw in UV visible spectroscopy or fluorescence spectroscopy, you are taking a cuvette or you are taking a sample holder, you are putting your sample and just scanning it. But here, before putting the sample, you need to do atomization of the sample. Okay, atomization and mostly vapor phase atomization. Okay, so how the dissolution is happening here? The sample containing metal particles is dehydrated. Here we are not studying aqueous solutions like the way we studied EV visible or IR not, EV visible and fluorescence spectrometry. Here what you are doing, the sample containing metal particles is first dehydrated by heat of flame and the solvent is evaporated. That is the first step. Okay. Then second, what you are doing? Vaporization. The heat of the flame vaporizes the sample constituents. No chemical change takes place at this stage. Chemical change should not be there. If it is there, then what is the meaning of studying the element? So you are doing it very carefully. The sample preparation of these atomic spectroscopies takes a longer time, sample preparation. However, till now, for the molecular spectroscopy, you have not seen this kind of sample preparation. You just take the sample, simply keep it in the sample compartment. So, vaporization is the second step. Then, at the atomization stage, the metal ions that were in the solvent are reduced to metal atoms. How you are doing? Metal atoms by desolvation, then by vaporization technique. Okay. So, by heat of the flame and action of reducing gas molecules, and the ions of sample species are decomposed and reduced to give atoms. Then the atoms at this stage are able to absorb energy from the heat of the flame. Then excitation of the atoms takes place. The amount of energy absorbed depends on the electrostatic force of the attraction between the negatively charged electrons and positively charged nucleus. Okay, this in turn depend upon the number of protons in the nucleus. So eventually what is happening, it is absorbing the radiation, atoms are absorbing the radiation, then excitation is happening. Then subsequently they are coming back down to the ground state or lower energy very quickly. Then emission of radiation is happening, the process we saw. This is the, I'm just reducing it little. So here you can see what is happening. This is from the nebulizer. First, from the nebulizer, the spraying process will happen by spraying the sample. Then desolvation will happen, means you have to evaporate the solvents. Then solid gas aerosol is there for the you have to make the sample volatile. Then gaseous molecules will come into picture. Then dissociation will happen, so that atoms will get created. Then ionization will take place and atomic ions will get created. At each state, whether this is gaseous molecule or atoms or atomic ions, the excitation can be possible, where excited molecules are coming into picture, excited molecules or excited atoms or excited ions. Then emission is happening. Then after emission, you are just that radiation which is coming back, you are just monitoring it through, it is passing through the filter or monochromator. Then your detector will be there to detect it. I will show you in the subsequent parts. And this is the structure of flame. Here nebulizer is there, means this sample is there. This I will show you in the next also, next part. Here the instrumentation for flame photometry. So the flame atomizer is very very important here. It converts the sample into excited atomic species and consists of the following part. That atomizer consists of the following part. One is nebulizer and mixing chamber, where the mixing or homogeneous solution happens. Okay, atomizer burner will be there. Here the fuel and oxidant burn into the flame, that gives that can be maintained at a constant form at constant temperature. So due to presence of this fuel and oxidant, the atomization happens. Then there will be a filter or monochromator which will isolate the light of the wavelength to measure the emission process. Then detector will be there, like the way we saw for the other spectroscopy methods. Then amplifier will be there, or which will amplify the signal, and readout device will be there. The similar way we studied for other spectroscopies, but here the difference is this part, this beginning part. Sorry, this beginning part. Okay, here sample, here analyte solution is there, this blue one, analyte solution is there. Here spraying is happening, this you are just spraying that analyte solution into this nebulizer. Okay, so here the molecules are coming into picture, mixing chamber it is. Then it is moving towards the flame. This is the burner. Here you can take your Bunsen burner, or you can have a specifically made burners for this kind of instruments to study. So everywhere you will not get flame photometry or AES, AAS. These are very very expensive, extremely expensive. One sample to study takes a long, means AAS, if I remember, many places you will not get AAS. It is very costly also. So this burner, through this burner inner, this molecules, this sample is going up, then flame, it is coming in contact of the flame, then their atomization and everything is happening. It is absorbing radiation, that molecule, that atoms or ions absorbing radiation, then the emitted radiation, it is going through lens, then you are having the filter which will just cut the other unwanted radiations coming out of it and make it some monochromatic way. That filter or monochromator will be there as a selector. Then photodetector will be there which will detect the part, then amplifier will amplify the signal, and readout device or output device, you will see the spectrum, that atomic spectrum you will see. Okay, so monochromator, detector and amplifier will be there to see the things. So coming to the applications of flame photometry, as we discussed in the previous parts, qualitative and quantitative applications are there. But let me put you in this way, that this flame photometry is very, very important. This atomic absorption spectroscopy, if you are just dealing with a pollution control board, or if you are working in some industries, or if you are very, very familiar with the atomic studies or element studies, alkali, alkaline earth metals, these are the best option to go for it. Yesterday we discussed that fluorescence spectroscopy. We discussed, yes, we can study arsenic, we can study lead, we can study fluoride by using fluorescence spectroscopy also. But there, the limitation is we need to have a chlorophyll, or we need to have a probe molecule which you want to put it in the solution to see the fluorescence. Indirectly, you can predict how much amount of your elements are present. Cadmium or whatever element you want to study, you have to attach to that fluorescence tag molecule, then you are studying. But here, directly, you can just attack the element itself. You can go for the elemental study here. But the cost is more also, as well as some limitations are also there with these things. But these are more specific for the alkaline and alkali metals. So this flowing, there are two applications, qualitative as well as quantitative. But qualitative, mostly we don't study the qualitative applications. Mostly is not done by the flame photometry. The flame photometric methods are widely used for the detection of your determination of alkali and alkaline earth metals in the samples that are easily prepared by the aqueous solutions. Some of these elements can be detected visually by the color in the flame. Okay, that is sodium produces yellow flame, I was telling. However, this method is not reliable. If you are just putting a flame test, this is not reliable. So best method is what? Best method is to use the flame photometer. Just a flame test doesn't help. Okay, I got a sodium here, or it is uh, means alkaline earth metal or alkali test, you are just uh, knowing what element is there. That is not the best method, but the best method is use of flame photometer, where there is some filter monochromator to separate the radiation, and with the wavelength characteristic of different metals from other radiations present in the solution or in the elements. So the mix radiations coming out of it will be just uh, uh, you can cut it by using filter or monochromator. So clean radiation you will be getting by using the flame photometer. Okay. But this method to carry out detection of element by flame photometry is fast, simple, and if carried out with care, quite reliable. Okay, however, there are some difficulties. It doesn't provide any information about the molecular structure of the compound present in the sample solution. It doesn't provide the molecular structure of the compound like the way for IR, for NMR, for mass, you can predict the structure of the compound. Here, qualitative analysis, qualitative application is mostly structural elucidation. Okay, quantitative part, many spectroscopies can do quantitative studies part. Okay, so here also the flame photometry, the quantitative application is there with respect to flame photometry. But if you specifically, just I would like to focus in this way, if you want to study soil contamination, water contamination is different thing, but soil contamination, if you want to study, then you can, this is the best way. Atomic absorption, atomic spectroscopic methods are best to go for the soil contamination studies. So the concentration of various alkali and alkaline earth metals is important in determining the suitability of soil for cultivation purpose. So mostly for agricultural researches, you can go for this kind of studies. So very often an analysis of seed leaves of the plant for K plus and calcium ion is carried out. So this gives an idea of the concentration of these ions in soil, which can be taken off by the plant. For agricultural purpose, the analysis of proper mixture of surface soil or subsoil is carried out to determine the fertilizer requirement for the soil. How whomever are doing agricultural research, they can answer your questions very well, but to have a knowledge on this, if your fertilizer whatever you are using, it requires certain elements in it, but you are predicting by using flame photometry that these are the elements present, so the absent elements you can get a note on the absent elements, so you can use the proper mixture of your surface soil or subsoils to carry out the or to determine how much what fertilizer is required for the soil. Okay, so mostly these quantitative applications are helpful as well as far as your agricultural research is concerned. So if you see, these are the list of elements and their characteristic emission wavelengths. You see, many elements are there. Yesterday, Ojas was asking about the arsenic detection. Arsenic, see, so easily by using this kind of detection, this kind of flame photometry also, you can also study the what presence of these ions or these elements, this calcium, bismuth, lead, then nickel, palladium. So they are having certain range of your wavelength lambda max and detection limit is there. See, here I would like to put you in this way that yesterday we discussed about the fluorescence spectroscopy also. There also you can study various elements. Okay. Here also you can study. But the thing is, once you are studying through this method, it's not the full and final that okay, this much is there. You can cross check with various other spectroscopic methods too. And main importantly, depending on the sensitivity of the spectroscopic method or depending on the like the way procedure to study these elements, the detection limit varies. This is the important point, detection limit. So suppose here arsenic, the 2.2 microgram you can monitor. Okay, but in other technique you may detect the arsenic amount where it is more, but there is limitation. To suppose this flame photometry, it is just up to 2.2 microgram. If a soil is having more than 2.2, then this is not suitable for that. So you may go for the another spectroscopic method to study it. So understood. You can't see, okay, arsenic I can study through flame photometry. I will just stop there. No, you have to set the detection limit also. Up to this quantity, I can use this spectroscopy. Up to that quantity, I can go for the other spectroscopic technique. So this is the broad way we can discuss. Okay. So methodology to adopt this quantitative analysis. Here I'm just making it more clear. Just a minute. Let me take some water. Okay, thank you. So, so by this time you got an idea that the general procedure in flame photometric determination involves preparation of the sample solution in a suitable solvent. You are just making the sample solution first. Then only you are spraying, na? Then only spraying into the nebulizer. So suitable solvent, then aspiring it into the flame. How you are doing that? By spraying that solution through passing through the chamber, means nebulizer. Then it is going into the flame portion, then measuring the intensity of the emitted radiation. Okay, radiation at the characteristic wavelength of the element. From the radiation intensity measured the concentration of the element in the sample, then you can determine. How you can determine? For AB visible also you have read that part. Again we will be seeing here. Those are not understood there, they can understand here also. However, the flame photometry is not an absolute method. It is an empirical and is sensitive to experimental conditions. You have to use the experimental conditions, you have to prepare the solution in a suitable way, pass through the nebulizer, then putting it into the flame. That you have also should do very carefully. I was telling you, every spectroscopy is having limitation. Okay. So, for this quantitative analysis, obviously you have to prepare a calibration plot. Calibration curve you have to prepare. How you will prepare the calibration curve? By using in UV visible spectrophotometry as well as your fluorescence spectroscopic methods. I told you how to prepare the calibration plot. Calibration plot you can do by using a reference sample whose emission intensity is known to you. Means suppose you are taking a molecule or a atom. Okay, you are increasing the concentration, in the x-axis, then you are just getting a emission intensity, then you are plotting it. It is one to one correspondence, so it is a linear plot you will get. Towards the end you may get a bent mark. Why? I told you that if you are increasing the concentration to a more extent limit, then there may be self-absorption, self-quenching may happen. But initially, this is the thing. So, calibration plot you can obtain by using a known sample. Then what you can do, whatever unknown sample you are taking, that unknown sample you are going to get a spectra for it, for the unknown sample. From the spectra you will get the emission intensity of that spectra. Then by getting the emission intensity you can just use this calibration plot to predict what is the concentration of the species. Okay, so this is the basic method for getting the concentration of the unknown sample. So these are the detection part. Then some example is there how to do it. Then other application, multi-element analysis also you can do. So summary we have come. So any doubt in this section?
Madam, can we analyze non-metal with this technique?
Everyone is there. Okay.
Hello.
Oh, many are there to get in. Okay. So I hope it is clear to all of you
Ma'am, am I
because
audible?
the mostly from the means last three classes we are reading about the spectroscopy. We are just discussing about its ground state, excited state, or quite often, like during graduation, you have not heard about these things that excitation, ground state, excited state, these parts. But here you are seeing every spectroscopy is dealing with that radiation and emission and absorption, all that. But the thing is, it is varying from process to process, methods are varying. If you want to study some elements, detection limit is varying. So if you are going for a specific spectroscopy, then only you can understand it very carefully. So come to the atomic fluorescence spectroscopy.
Ma'am,
See, 10 photometric. Huh?
ma'am, can I
Hello,
ask a
someone is
question?
there? Okay, it's not. So come to this uh, atomic fluorescence spectrometry. Okay. So in the previous unit, we discussed about the flame photometry, that you have learned about the analytical method based on the emission of radiation by the atomic species that have been excited with the help of thermal energy of the flame you are using there. In this unit, you would learn about another atomic spectroscopic technique. However, in this technique, what is the difference? The excitation is caused by the electromagnetic radiation and it is called atomic fluorescence spectrometry. Atomic fluorescence spectrometry, as will monitor the fluorescence emission from the excited state. Again, by the end of this unit, you will be more clear on this subject. Okay. In A phase, that is atomic fluorescence spectroscopy, the gaseous atoms obtained by the flame or electrothermal atomization are excited to higher energy levels by absorption of electromagnetic radiation. Are you noting down that here one thing that due to this here also flame you are using or any electrothermal atomization process you are using. If you remember that electric arc or plasma therapy, all that things are there for the atomization. That part you are doing here. But after atomization, that are getting excited to higher energy levels by absorption of electromagnetic radiation. and the fluorescence emission from these excited atoms is measured. Like the way we have already studied the fluorescence spectroscopy. Here also we are going to do that. But there the difference was you are taking the sample, putting it cuvette and just measuring. Here before that the atomization process needs to be done. So this technique incorporates the aspect of both absorption as well as emission. Obviously, there is absorption means it will go to the excited state, definitely emission will happen and it will come to the ground state. So one by one we will move. Atomic fluorescence spectrum. An atom contains a set of quantized energy levels that can be occupied by the electrons depending on the energy. Okay. The atoms obtained by the process of atomization in a lower temperature flame are primarily in the ground state. After atomization, it will be in the ground state. When exposed to intense radiation source consisting of radiation that can be observed by the atoms they excited. The source can be a continuous source like a xenon lamp. Last class we discussed about xenon lamp that we are using in the fluorescence spectrophotometry, or a line source like a hollow cathode lamp. So the source can be different depending on the spectroscopic tool. So the radiationally excited atoms relax back to the ground state accompanied by a radiation. This phenomenon is called atomic fluorescence emission. Okay. See, the thing is, here the thing is, you are just putting radiation for the excitation. But in flame photometry, that's thermal energy of the flame is enough for the excitation. So, at the processes, the methods of studying the things, the method of sensitivity, the of the methods also varies. That is why detection limit for the elements that you are going to study also varies. So though these processes, all the processes involves excitation, emission, all that things, but due to methodology of these processes, the methodology varies from this process to that process. Okay. So this is about atomic fluorescence emission, and the plot that you are going to get, that is intensity versus wavelength, that is your atomic fluorescence spectrum, the way we discussed there. Okay. So here also atomic fluorescence transitions are of various types. Resonance fluorescence, Stokes direct line fluorescence, stepwise line fluorescence, two-step excitation double fluorescence, like that. But the concept over there is same. That is, it is going to excited state and just coming back with the radiation. That is the thing. But while studying the NMR and all, this part is not there. This radiation emission part is not there. We'll just see in that section. So, what is the principle of this atomic fluorescence spectroscopy? That atomic fluorescence spectrometry is the analytical method based on optical emission from the gas phase of atoms that have been excited to the higher energy levels by absorption of the radiation. Okay, so it incorporates aspects of two, both the things, that is your absorption and emission of the radiation. In atomic fluorescence spectrometry, the analyte which you are going to study is brought into an atom reservoir, which could be a flame or plasma or glow discharge or furnace. Okay. Then after atomization is excited by focusing a beam of monochromatic electromagnetic radiation emitted by suitable primary source. Then the radiation source can be a continuous type xenon lamp or can be this. See, when the question is coming, what is the principle of atomic fluorescence spectroscopy? What is the principle of UV visible spectroscopy? What is the principle of IR spectroscopy? I think by this time you all are confident enough to write the principle. Because if you understand the thing, the process is almost more or less same for everything. Process the is same, but the source, but the excitation parts or emission part, these are different. So you can write tune your writing accordingly. So you need to understand one or two spectroscopy very carefully. And this always I am saying the visual and audio thing is having a large impact. If today exam is there, if you are sitting with the this what to say material, then nothing will come to your mind. You will be feeling what is this spectroscopic method is very difficult subject. What madam was teaching on that day, it was just bouncing. I am not able to understand these things very what is this is chemistry or what? No chemistry is there, only methods, these things, that things. It will be very difficult for you to understand. Today you will think, okay, today I will read this. You will sit for some time, then this today will go. Okay, no problem. Tomorrow I will start reading. Then tomorrow you will sit, then again tomorrow will go. It will happen like this. But if you are attending the class, if you are hearing something, that hearing impact is there. Okay, I understood these are the things, these terminologies I heard, this is that, that is that. Then something you can correlate while reading. Obviously, these classes are not enough. We'll just show you the path, but you have to walk of your own in that. So you have to read a lot for that. As I was telling you, here everything. See what is written as you have learnt above. This is happening, that is happening. So nicely it is written in your this material. So the emission, fluorescence emission may be of same wavelength, that is resonance fluorescence. When it is coming back to the ground state, it may sometimes emit the same energy, but it is very, very, very rare because during the absorption process, it absorbs a lot of things. That is why it comes in the longer wavelength region. Then fluorescence intensity and analyte concentration. These two things are having a very good relation. That is fluorescence intensity, if it is more, then analyte concentration, you can predict it to be more. Okay. So this absorption of radiation to generate the excited atoms happens. Then de-excitation of the emission part also happens. Okay. So the fluorescence intensity and this thing is both interlinked. But here, if you see, as I was telling you, the longer concentration region, here you are seeing a bent over there. Okay, bent over there. It is not one-to-one correspondence. That is intensity and concentration is not having one-to-one link because of your. I was telling you about the self-absorption and the quenching. Last class also we discussed. If many people have not understood that, here also you can be clear, very clear. So this thing is valid only at low concentration of the element because there is proportionality at the low concentration. At higher concentration, when the fluorescence emission is high, part of the emitted light will be absorbed by the atoms in the ground state. What does it mean? If you are having, suppose 50 molecules in your sample. 50 molecules are there. You are exciting 50 molecules. Out of that, some will not get excited, some will excited, like suppose 45 molecules have excited. Then you are going to get emission from the 45 or so. But if you are taking too much high concentration, sometimes what happen, like suppose 200 molecules are there. Out of 200, some 120 or something is getting excited. Okay, when they are emitting certain radiations, that emitted radiation also can be absorbed by that remaining 80s or remaining 80s. Among that, some 60s may absorb that emitted radiation also. Again, they may go up. Again, they may go up. Okay, so that is what is your self absorption. That is what is your self absorption. So that is why the intensity may reduce. Last class we discussed about this. Self absorption is a very important factor, but reduction or quenching of the your fluorescence also. Okay, of the intensity. So it will lower the intensity of the emitted radiation and the proportionality is lost at the higher concentration. Further, the efficiency of fluorescence emission, that is 5. Quantum efficiency, in the last class we discussed quantum efficiency. The efficiency of the fluorescence emission is lower if the atoms in the excited state lose their energy by radiation-less path. Again, they may lose their energy by radiation-less path. How? And by collision with another atoms. If collisional quenching is there, then they will bombard among themselves. Then they will lose energy in that way also. So intensity may decrease. Where the energy of the excited state is transferred to the vibrational levels of these atoms. Vibrational levels may observe certain radiations. But since though these vibrational energy levels, rotational energy levels are not quantized, it is not going to take part in the process. So this deactivation of the excited state may happen and it is known as your quenching. Means quenching means is all along the decrease in the intensity of the fluorescence or intensity of the any process, any spectral process. So the proportion of deactivation by quenching mechanism can be decreased by surrounding atomization flames by a noble gas like argon or by using non-flame methods to convert the sample into atoms. If you are using some, see, in presence of oxygen, if it is coming in contact of oxygen, last class we are discussing dissolved oxygen also a factor for the quenching because these oxygens are generally in the triplet state. They will come in contact of the molecule, they will quench the process. So if you are using some noble gas, then it may reduce the quenching process. Okay. So instrumentation for atomic fluorescence spectrometry. So far you have seen that atomic fluorescence spectrometry concerns the measurement of fluorescence emission of the atomic species that have been excited with the help of suitable electromagnetic radiation. So this in turn requires that vaporized atoms of the analyte should be in the ground state. Then only excitation will happen. Okay, so thus in the atomic fluorescence analysis of samples, the analyte atoms needs to be desolvated, vaporized and atomized at a relatively low temperature. That process is done, then only electromagnetic radiation will put into picture, then excitation will happen. So this can be achieved with the help of a heat pipe, flame, graphite furnace, or any atomization process. Okay. So once the vaporized atoms are generated, a hollow cathode lamp or a tuned laser usually provides the monochromatic radiation for resonant excitation to promote the atoms to higher energy levels. Okay, so there will be a radiation source, atom reservoir, monochromator, detection system or detector will be there, amplifier and reading out device will be there. So this is the block diagram where you are having radiation source, atom reservoir, like some flame through flame or through furnace, atomization is getting done. Then wavelength selector, here you can put filter or monochromator depending on the radiation you want to get into the picture. Then you will have detector which will detect the radiation, then signal processor, it will amplify the signal, and your readout device will be there, output. This is the general block diagram. However, block diagram looks so simple. However, here you see the source supply will be there. Here is source is there. Source means you will be having nebulizer, then flame will be there. You can see here flame is there. So atomization process is happening in this compartment. Then radiation, so through the source you are supplying the radiations also. Then you are going to get some emitted radiation which is passing through the lens. Then mirrors will be there, grating mirrors will be there, which will, this is just a process of amplifying the things. Okay, converging the things into a particular part. So depending on the method of your spectroscopic tool you are going to use, you can tune it to get a better signal. That always you can do. Then the detector is there, then you are having a output device. Okay, so radiation source, here we are using your tungsten halide or deuterium lamp. Okay, also you can use hollow cathode lamp. This is the hollow cathode lamp. You are just in the block diagram we are seeing, okay, this is the source, that is the this, but in the instrument it is so complicated. If you see the lamp, this is like this, so it is having many things in between that also. So in the block diagram you can just mention that when in your exam it is coming, write the instrumentation process for the fluorescence spectrometry or for the AFS, you can write do the block diagram, no problem. Instead of doing these things you can do the block diagram. Okay, so there are various things. Then atom reservoir. Atom reservoir, as mentioned in the AFS, the analyte sample is to be converted into atom vapor in the ground state before being excited by suitable radiation. Then the container or cell having these vaporized atoms is called atom reservoir or atom cell. Okay. So the atom cell is there where your atomic atomization is happening. Then you'll have monochromator through which the radiation it is passing through. You are just making it monochromatic. Then detector is there and readout device. The simple way which we have already studied in various methods. So coming to this application part, application of atomic fluorescence spectroscopy. This is very important. This atomic fluorescence spectrometry is you can use in various fields. Okay, it has been used in analysis of more than about 60 different elements present in diverse variety of samples. Okay, the general use of a phase is to determine concentration of element in samples, that is which say elemental analysis. Okay, favorable conditions for some elements, detection limit, it is in the range of your 10 to the power minus 18 gram. It is in the attogram scale. I was just putting some light on that section. I was telling you, detection limit is very, very important. You can study these elements through normal fluorescence. You can study these elements through plain photometry. You can study some elements through AFS. But detection limit you have to see. If you want to do further research on this topic, you need to see if you are in an area where soil contamination with arsenic is more or with lead is more, then you must check which detection method you should use. Though that element you can use some with different methods, but you need to find out that. Okay. So that is the major thing I was wanting to tell you. So, in typical quantitative determination, using a high intensity hollow cathode lamp of the element to be determined as the radiation source, a series of solution of the metal ions of varying concentration are prepared and aspirated into the flame, and the corresponding fluorescence intensity is measured. So a plot of fluorescence intensity versus concentration of the metal ion is plotted. What I was telling you about the calibration plot. Calibration plot. So this curve is linear at low concentration metal ions, but it is convex at higher concentration. See, in your material, if you are going through the material itself, you will be more clear. For exam point of view, there is no problem at all. The fluorescence intensity for the solution containing the analyte is unknown concentration is measured, and the concentration of the metal ion can be determined from the standard curve. But the point which we are discussing from a long time, how to do quantitative analysis. See in how many areas you can use this AFS, that is atomic fluorescence spectrometry. You can use in this many areas, like in clinical section, the analysis of lead, mercury, arsenic, bismuth, all these things you can do in urine, in blood, in tissue, in nail, hair. Okay, then copper, zinc, palladium in blood serum and urine samples, that also can be studied. Then environmental point of view, determination of mercury at 1 nanogram per liter level. See, wherever you are dealing with these elements, you will find some detection limits in any method you go, you will find the detection limit. Determination in the femtogram scale or attogram, whatever it may be, it will be mentioned. And it will be in the ppb scale or ppas scale, it will be mentioned. So as far as agricultural point of view is concerned, analysis of dairy, wine, feed, meat, cigarettes, and other products for this element study can be done in if you want to study the elemental analysis in that particular things. Then geological and metallurgical aspects, analysis of ore, rock, mineral. It means it is having so vast application. This AFS. I had not practically used this AFS, but AS was there in my previous institute where I was working. AS was there, atomic absorption spectrometry, but this AFS is having it is very useful. Then pharmaceutical aspect, if you see, then determination of these elements can be done in any ingredients or fillers. Then petrochemical application is also there in fuels or lubricants or crude oils. You can also go for these elemental detections. Okay. So here if you see here your detection limit is given. Which elements you can study through atomic fluorescence spectroscopy? What is its corresponding emission wavelength? Then what is its detection limit? Up to what limit you can go for this spectroscopic method? That also you can see. Okay. Interference, there is always interference, okay, of your chemical interference or your radiation interference. Any error due to your experimental error will be there, interference will be there, or chemical interference will be there. That interference means some other components, some addition of interference of other components may happen, or it may affect the normal procedure of the detection. Okay. Then coming to merits and limitations, the main advantage of the fluorescence detection compared to absorption measurement is greater sensitivity. I was repeating this one in the last class itself. Okay, as compared to absorption, your emission process fluorescence detection is very sensitive. Why? If you remember the absorption process, since it is ratiometric, you don't have to do anything with the intensity of the source. If you are increasing the intensity of the source also, it is not going to affect. But your sensitivity you can tune by using your, if your intensity of the source you are increasing, amplifying, and here this fluorescence source you are using general lamp, which is very good, and good intensity will get by taking lower concentration of the sample, like 10 micromolar concentration of the sample you can get. It's not like you are just taking a full hand of fluorescent molecule and just putting it in the fluorescent fluorimeter. You will be getting the spectrum. No, absolutely, you will not get zero. You will not get anything. You have to take very less amount, like milligram quantity. If you are taking, then you are making the solution of micromolar concentration region, then only you will get good spectrum, then only you will get a good spectrum. Okay, so these are very sensitive, and because the fluorescence signal has a much lower background uh, as compared to one observed in atomic absorption method. It is always have lower background noise. Okay. Further, the interference are also less because the intensity of the source is so high. It will just neglect the other interference also gets neglected. It exhibits its greatest sensitivity of the elements having higher excitation energies. So A phase offers distinct advantages for some metals and metalloids like lead, cadmium. These are very important to study. This lead, arsenic, mercury contamination nowadays is so much that the advantage you can take use of these spectroscopic advantages to study these elements or the contaminations in soil or any thing you want to study. And the detection limits are similar to those for AS and AES. AFS detection limit are almost more or less same as that for AS and AES, but vary for different elements. Better sensitivities and much lower detection limit are obtained for favorable elements. So some elements you can detect at lower detection limit also. Means if it is available in the lower concentration also, you can detect through this technique. So now from this line you are clear that this AFS, even if it is able to detect very small quantity of the thing, but this is also preferring to certain elements. To certain elements, it's not like all elements with lower detection limit it can sense. There is a particular limit to everything. So the linear calibration curves that often extended over a wide range. So they may be valid over a high as to 4 to 7 order of magnitude, and the samples in solid, liquid, gaseous state can be analyzed. Although most of the samples are converted into liquid before analysis, then only you can do the spraying of that thing up to the nebulizer. Then only it will have through flame or electric arc. You can do atomization. Then subsequently you can move on. Okay. When combined with the separation techniques such as chromatography, the method can provide more information about the chemical form of the analyte. This thing you can note while studying the separation technique. Another chapter is there, chromatography. You can that time you can correlate and understand it in a better way. So, though this AFS offers a number of advantages, there is some limitation also. So AFS requires combination with chromatography to provide information regarding chemical form of the analyte during the chemical separation. Mostly what is happening till now, whatever you have seen in the flame photometry or AFS, you are seeing the chemical form of an analyte. We are not able to know chemical form, in which form it is available. Okay, that can be better understood through chromatograph. If you are combining the FS and chromatography, then you can go for the predicting what chemical form it is there. That you can study in your separation method technique chapter also. So the sample preparation specifically for the solids is often very tedious and time consuming process. The one I was telling you, that sample preparation for these atomic spectroscopic methods is very important and playing a crucial role. You will be seeing that you have to prepare the sample, spray it, nebulizer, it will pass through. How the atomization is happening means up to the atomization excitation, you are having a lot of work to do before it is getting scanned with. Okay, so the analysis may involve chemical interference due to the chemical reactions between the analyte and other components of the sample that may reduce the number of free atoms produced, as well as you can, as we saw at one point, you can use noble gases. If you are using noble gases, then some chemical interference you can avoid and you can get a good result also. In analysis of many samples, it may be necessary to correct for the spectral interference, especially when continuous sources are used. The technique is limited primarily to detection of metals and metalloids. Understood? It is limited to metals and metalloids. So there are limitations. Hey, you see here one example I was telling you, na? Wherever you will find these SAQs, okay, questions, before that your answers will be ready. In this material has been designed in such a way that why it is not getting widespread acceptance as an analytical technique, because these are having many limitations. So if you go through the material, I had observed it very carefully that wherever SEQs are there, before that you are having answers to it. Okay. So, okay, we came to summary. In atomic fluorescence spectrometry, the gaseous atoms obtained by the flame or electrothermal atomization are excited to the higher energy levels by absorption of the electromagnetic radiation, and the fluorescence emission from these excited atoms is measured. After excitation, the radiation emission is there, then you are measuring the fluorescence. The fluorescence emission can occur through different pathways. Accordingly, we have different type of atomic fluorescence transitions. The common type of atomic fluorescence transitions are known as your resonance fluorescence and Stokes direct line fluorescence, stepwise line fluorescence. These are various techniques, different type of fluorescence. The intensity of the fluorescence radiation is measured at right angle, which we had already studied in the previous class, to the direction of the incident radiation. Why so? Because we want the transmitted lights to get avoided. We want a specific quantity, we want a specific wavelength of radiation to collect into picture. Okay. And it is correlated to the concentration of the element present. So, forming the basis of quantitative analysis, you need to have a good correlation between concentration and the intensity. The quantitative atomic fluorescence, the spectroscopic determinations of the instrument is generally standardized by the calibration curve. It is applicable for most of the spectroscopic method which are getting used for the quantitative analysis. Okay, calibration curve is very, very important. So the instrument used for AFS consists of your atom reservoir, which may be a flame or a furnace, then a primary source emitting the characteristic absorption radiation of the element being determined. A monochromator will be there, then a detector, then a signal processor will be there. So by this time, by seeing these many spectroscopic methods, you may have got a clear idea about more or less all are interlinked, but the methodology, instrumentation, and the detection limits for different things are different. Okay, so now you can discuss any question if you are having. Okay, here one question is there from Ojas. Which method is best among AES, AFS, AS to deal with chemical interference? Okay, if you ask me this question, as far as my knowledge is concerned, AFS will be the best among these three things. Why? If I want to justify the thing, then what is happening? AAS is the atomic absorption spectroscopy. AFS is the atomic fluorescence spectroscopy, where the source radiation we are using is of highly intense radiation we are putting into the sample. Okay, so that is why the interference, the effect, this chemical interference will minimize. Maybe the time you asked me question, before that itself, I told you in my material that while discussing the interference, that time it was written over there. AFS, the noise due to this background noise is very, very less. Okay, so AFS is a good technique to be to avoid the chemical interference. So,
Ma'am, hello.
what it is written?
Ma'am, am I audible?
Mm, Practical career registration. I don't have idea. Absolutely, I don't have no idea about the practical registrations because. Uh, okay, thank you, Ojas. So because these all you can coordinate with your coordinators. They can tell you better. The coordinators, the respective regional centers, you can just. Am I audible? Who is telling? Deepti Ranjan.
Ma'am, am I
No,
audible?
today you are not audible. Can you
Am I?
increase your voice?
Yes, ma'am. Am I audible?
Or I am having some mic problem, no? No,
Am I,
it's fine.
am I audible now, ma'am?
Very less sound is coming. Is it happening to me or other people?
Hello.
Tell.
Hello, ma'am.
Tell.
Ma'am, why the relaxation time in the atomic spectroscopic methods is longer than
Anyone
the.
is getting his question?
Yes, ma'am.
Actually, why your voice is so low today?
I don't know, ma'am. It's really.
Or I am having some problem? Or oh,
Yes,
okay.
ma'am.
Just a minute. Let me see. Oh. Okay. Till now?
Audible now?
Yes. Oh, it is in speaker. Okay, fine. Tell.
Okay, ma'am. You said about molecular spectroscopy, the relaxation time was in femtoseconds. Uh, but
I
in
have not because it is a wrong statement.
ma'am,
By the time you are telling, immediately I am just replying you that relaxation process is not a factor.
then what was the femtosecond sentence? I don't remember that.
Okay,
Actually,
absorption. When a molecule is absorbing radiation, it is
okay,
going
okay, excitation. Okay, okay,
step
excitation.
that is of femtosecond. That is
But
why. So listen. You need to understand here. That is why the absorption processes are so fast that your internuclear distance is not changing. That is why you are getting straight lines. You are representing all the transitions in straight lines. Okay. And it is something to do with the Frank-Condon principle. If you remember my class, I was
yes,
explaining
ma'am.
you Frank.
Without changing the distance.
Yes.
Ma'am, is the relaxation time will be same for molecular and atomic spectroscopies or different?
Uh, a relaxation time, it may be almost same because today also while teaching you the atomic absorption that atomic fluorescence spectroscopy, I have highlighted that point that it is happening in the 10 to the power minus 6 to minus 9 second. In the fluorescence normal molecular spectroscopy also, it is happening in the 10 power minus 6 to minus 9 second. See, the thing is, the most effective difference over here is here you don't have vibrational and rotational energy levels are not quantized. That is the major difference you can find. Otherwise, mostly as far as method is concerned, more or less it is these both are comparable to each other. Okay, mostly both are parallel to each other, but here these energy levels are not quantized. That is why you are getting a this, line spectrum or a sharp spectrum. There you are getting a broad spectrum.
And ma'am, if the relaxation time is almost same, then would not it affect the line width? Means line width into time. Actually, a line width into relaxation time is greater than equal to h by 2 pi. I have seen somewhere this expression actually. If relaxation time is longer, then we will get a sharp peak, and if relaxation time is short, then broad peak will appear.
No, I don't agree with this because if
Line width.
you see simple concept logically, if you think fluorescence and phosphorescence, okay, fluorescence is happening in the time scale of 10 to the power minus 6 to minus 9 nanosecond time scale region, okay.
Yes, ma'am.
Here phosphorescence is happening 10 to the power minus 3 to 10 to the power 2. It is taking long time, right?
Yes,
Phosphorescence.
yes,
But
ma'am.
yesterday I was showing you two graphs, if you remember, the spectrums of the fluorescence and phosphorescence. Broadness is not depending on that, or the line
Yes,
switching of line is not depending on that. It morely depends on the energy spacing, and the vibrational rotational energy levels are quantized or not. They mostly depend on the level
yes,
spacings.
ma'am. I understand that aspect.
Hmm.
Actually, in molecular, the electronic transitions are accompanied with the vibration as well as rotational transitions.
No, no,
For
that part
which,
is different. That part is different. I am
for
just
which we
making
are
you
getting that
understand
broad
about the
signal.
time. I'm just making you to understand about the time.
Relaxation time. Yes, ma'am.
Fluorescence,
I was
yes, fluorescence takes a long time. Even then, the broadness wise, it is not differing much. So I would like to put you in that way. So Krishnendu Day, can I get recorded videos of this session? I don't have any idea because this recorded videos and the access to this classroom RC Bhubaneswar is available to me only for the class. I am not entitled, or I have not got any permission to share the recorded videos. You can consult RC Bhubaneswar. Okay. Rajkumar, Dr. Rajkumar, please tell us the flame photometer working on this which law? The principle you are talking about, flame photometer, the flame photometer, the principle you are talking about. Otherwise, it is having the absorption as well as emission processes involved with this. It is there is no like Bell numbers law or the Franklin principle. Everything is applicable because this flame photometer is the working principle is it is having the absorption of energy and excitation, then followed by emission. The principle of this flame photometer is this. The only difference over here as compared to any other technique is there will be you are using this flame as a source of energy for the atomization process, then for the excitation of these atoms, and then further followed by its emission.
hello.
Ma'am, hello.
Hmm. Tell.
Hello, ma'am. Ma'am, I just have a question that can I get recorded videos of these sessions
Ah,
afterwards?
just now I answered that actually I am
Actually,
not.
my internet was slow.
Internet is slow. Okay, I can
Yeah.
understand the limitation of online class. I can understand that because the same person me, I will explain in my classroom blackboard teaching in a way, and here also it is something different way because we need to put our heads to see how much comfortably we can teach you. But there is some limitations with that, but I am helpless in this regard because I don't have any permission to share the recording videos with you. I am just opening the classroom RC Bhubaneswar link just to take the class. If you want the recordings, you can contact RC Bhubaneswar or your nearby coordinated centers.
So, okay. So, ma'am, these sessions will be purely theoretical lessons, right? If
Yes,
I'm not wrong.
yes, these are theoretical lessons. You are having four theories, right?
Yes, ma'am.
four theories in the first class itself. I told you there was maybe some gap. See, these four theories you are having. Practical session we are not doing now. Out of this four theory, the basic analytical chemistry MCH-001, which will be little easy for you because basic analytical chemistry you know from the beginning, conductometry, pH metry, that things. Then separation methods you will read about chromatographic techniques there. So it will be little unknown to you, but you can study well. Spectroscopic method is something not exactly chemistry type, it is some detection methods only. Then electroanalytical methods also you can, it will be easy for you. That is gravimetric analysis, then pH meter, conductivity meter, colorimeter, then different techniques will be there. So once you are finishing the spectroscopic methods, then half a course over. You can imagine half a course over. This is the most difficult one you are having with.
Ma'am,
Because if you
Okay,
see
so
here,
ma'am, can we get these PPT?
PPT. Oh, you were not in
Yes,
my
ma'am.
first class. I guess so because see, I am not preparing any PPT, just only 9 slides. I am not prepared because I thought you all are having materials, IGNO materials with you. So I thought in
Yes,
what
ma'am,
way
we
it
do
will
have.
be easy for you. So I am just following that materials so that there will not be any communication gap with me and you, and I can just better way I can teach.
ma'am,
Otherwise, otherwise, just I want to say you here, one spectroscopic method here written in one units. Frankly speaking, if I am taking IR spectrophotometry offline mode, we used to take 10 classes. Raman spectroscopy 10 classes, UV visible also same. So these are very vast topics actually. In order to cover in class, we are just putting you a glimpse of idea about that. I think this is the motto of this spectroscopic method to have you an idea of everything. Okay, tell.
ma'am, in fluorescence spectroscopy,
Hmm.
we need some fluorescent probes to be attached at the metals to be detected in the fluorescence spectrometer.
Yes.
But in this particular technique, we don't need that to detect that particular metal.
No.
How can this be possible? How can this be a metal particularly can be fluorescent or radiating some fluorescence?
No, radiating not. See, sodium. As such, if you are taking sodium, you are not able to study through this fluorimeter, fluorescence, just making it a solution. You are just doing atomization of it. If you remember your flame test, you are doing
Yes,
putting
ma'am.
a flame and making it the atomization of it. That atom of that element, okay, due to its electron transition, it is showing you color. It is not exactly the fluorescence spectroscopy we are studying. I was just putting you in that way that the method, the methodology, that is excitation, emission, radiation emission, these are same. But it need not to be that elements will show you in solution phase because solutions will be surrounded to it. Then there other physical concepts are coming into picture. That solvent cage, it is forming near to that and other things are coming into picture. Okay, just
Uh,
today I will stop here. Okay, because time is already there. I have to also go to my room, right? I am in the office. Oh, just one question is there. Which type of chromatography is generally used for flame photometry? Absolutely, I don't have idea because chromatographic technique, I had not gone through that part. Uh, it is better if while studying the chromatographic technique in the next After my class, one more sir will be taking, Prakash Sahu sir, a chromatography class he will take. You can ask him. Okay. So thank you very much. So I'm just
Thank
finishing.
you, ma'am. Thank
Okay, conclude.
Thank you, ma'am.